In this video, we explore one of the most fundamental shapes in statistics. Bell-shaped distributions appear everywhere, from natural phenomena to human behavior. Let's take a closer look at how normal curves are used to model these situations. To prepare for normal curves, let's briefly revisit histograms. The height of each bar in a histogram represents how many data points there are for an interval. For instance, in the dot plot, there are 5 dogs whose weight is at least 10 pounds, but less than 15 pounds. In the histogram, we see that the first bar has a height of 5, indicating that 5 dogs have a weight of at least 10 pounds, but less than 15 pounds. Neither graph is necessarily better, but they do different things. For instance, the dot plot shows us that 2 dogs weigh 34 pounds. The histogram does not show this information because these 2 dogs are lumped together with dogs of other weights in the interval between 30 and 35. But if we want to know how many dogs weigh less than 30 pounds, it would be easier to use the histogram because we could just add the height of these 4 bars. We see that there are 25 dogs that weigh more than 10 pounds but less than 30 pounds. That would be easier than counting every dot in the dot plot. But the important thing is that both graphs show the overall shape of the distribution of data. Just to clarify, we can use this histogram to count how many students there were in the study. Adding the height of each bar, we get 38 students. Or we could determine how many students earn a grade of 80% or higher. And that would be 19 students. We can often describe the shape of these distributions with certain names. Distributions with a long tail to the left are called skewed left. With long tails to the right, they are called skewed right. And if they are somewhat balanced on both sides, we can say they are roughly symmetric. Statisticians often use curves like this one to approximate the shape of their distributions of data. They do this because there are some powerful tools that they can use with these curves to help them analyze their data. In particular, the bell-shaped curves that approximate the shape of some symmetric distributions are called normal distributions. Normal distributions have a single peak, and that peak is in the middle, and balanced tails that stretch out to the left and to the right. We can make a nice sketch of a normal distribution only knowing its mean and standard deviation. The Greek letter mu is an abbreviation for the mean, and the Greek letter sigma is used for the standard deviation. Let's sketch a normal curve with a mean of 30 and a standard deviation of 2. We'll start with a horizontal axis with 30 in the middle. Then mark your axis 3 times on both sides of the mean. Do your best to make those evenly spaced. For each tick mark to the right, add the standard deviation And for each tick on the left, subtract it. The peak of the normal curve will naturally be in the middle, and by the time we get to 3 standard deviations away from the mean, we want the tails to be pretty much all the way down to the axis. To get the bell shape, think of the top as sort of a frown bending down. This type of curve is called concave down. But then, when you get to 1 standard deviation away from the mean, the curvature switches to concave up, which is more like a smile. Then, by the time you get to 3 standard deviations away from the mean, the tail has not crossed the x-axis, but it is very, very close to it, just barely above it. So here's my frown. When I get to 28, I'm going to switch from a frown curvature to a smiling curvature and end up almost to the x-axis by the time I get to 24. Now we'll try to make it symmetric, but since we're sketching, we'll be forgiving with our drawings here. So here's my frown until I get to 32. Then it changes to a smile. It should be almost all the way down by the time I get to 36. Computers can, of course, make these more precise, but sometimes sketching things by hand help us understand a new concept. I'm in the Desmos graphing calculator, and I will be changing the mean. So notice when I increase the mean, like I'm doing right now, the only thing that changes is that the graph is sliding to the right. Then as I decrease the mean, like I'm doing right now, the graph moves to the left, but the shape of the graph is staying the same. So changes in the mean just move the graph left or right, but the overall shape is the same. So the mean is in the middle, so in this case, the mean is 0. Now I've increased the mean to 4, and we notice that the normal curve has moved to the right. Now let's look at the standard deviation. The standard deviation tells us how spread out the data is. So when I make the standard deviation smaller, the data will be more bunched up near the mean, which changes the shape of the graph. So here I'm making the standard deviation smaller, which makes the graph narrow and tall. But now, as I make the standard deviation larger, that makes the graph wider and shorter. A smaller standard deviation means the data is less spread out, which makes the graph narrow and tall. A larger standard deviation means the data is more spread out, which makes the graph wide and short. Both of these graphs have the same mean, but the first one has a standard deviation of 2, and the second one has a standard deviation of 3. Notice that the graph with the larger standard deviation is more spread out. Here's another visual of that same concept. It shows 3 normal distributions, all with a mean of 0. The blue graph has a standard deviation of 0.5, so it's tall and narrow. The green graph has a standard deviation of 1, and the red graph has a standard deviation of 2. And we can see that it's wider and much shorter. In this video, we learned how to make a sketch of a normal curve. knowing only the mean and the standard deviation of the population. I hope these examples have been helpful. This is Mr. Ela, signing off.